Hereby, I open this academic ceremony in which Naveen Balakrishnan will defend the academic thesis, Sustainably Dyed and Functionalized Biobased Polylactic Acid Fibers for Textile Applications, an in-depth investigation on the effect of multifunctional colorants on the properties of PLA. May I invite you to present a summary of your study and the conclusions of your thesis.
Thank you, Pro-Rector. Hello. First of all, a very nice day to everybody. Thank you for all joining in. Now I would like to start with a short presentation on the sustainably dyed and functionalized bio-based PLA fibers for textile applications, which is also the part of my dissertation. And I would like to start with a short outline with an introduction and state of the art, followed by a problem statement, which I worked on, and then a short conclusion. So I'll try to keep it short to get it done in 15 minutes. Let's hope for the best. So as a short introduction, so if you look at textile industry in Europe, it's quite huge. So it has a market of around 160 billion euros. And when you look at the textile world, a whole part of it is man-made fibers, which is almost like 80 million tons is actually made out of man-made fibers. And then when you look, PET is one of the major players, which is also known as polyesters. As most of you might know, it is from fossil-based sources. And when you look at the textile field, it is quite huge, and especially when we look at apparels for textiles, colorants is one of the most commonly used additive, which also has a huge market, and what we use now is mostly fossil-based and also azo-based and so on, which are also making it more toxic and not really sustainable for us to use. And when we look at how dyeing is applied, for example, you have majorly two types of dyeing approaches. So one is you prepare the textiles already, or the yarn, and then you dye it in a bath, and then you have the dyed fabric. And the second approach is to mix the colorant in the material before you make the yarn. And this is called as dope dyeing. And when you look at the advantages and disadvantages, so for the bath dyeing, it is more commonly used. It's easy to change the color because I just need to take the dye bath out, clean it, put in the new one, it's done. And when I use additional chemical, but then the disadvantage is that I have to use a lot of chemicals to make sure the color sticks to the surface of the fabric that I use. And also there's a lot of dye loss. And then a lot of these times this water just goes into the drinking water sources, which also pollutes most of the rivers and so on. And when we look at dope dyeing, the advantage here is that we don't have any chemicals that we need, so it's normally good, and it's close to no wastage of the dye, because it's a more continuous process. And it's done for production of large quantities, but changing the color is difficult because cleaning the extruder means you need like huge amounts of material to clean the color to change it. And then we need high temperatures for this process. And when we look at a short introduction on the dyes, the first use of dye has been reported in 30,000 BC, so it's quite old. And even in book of written records, it's been in like 2600 BC. That's already evidences of bio-based colorants. And then in 1860s, closer towards the second half of the 19th century, there has been development of fossil-based colorants, or like azo compounds, which led to most of the colorants that we are using right now, which are all fossil-based. And now, because with the questions of sustainability and so on in mind, the options is we are now looking for some alternatives as to what do we do. So as you see, that's a short summary of whatever things we are facing right now. We are quite dependent on oil-based materials for both polymers and colorants, and the process we are using for dyeing is also not the most sustainable because of dye loss and water pollution. So with this in mind, the goal of my thesis was to develop PLA-based textiles using the dope dyeing process with bio-based or potentially bio-based colorants to show where are we with these materials right now. And this project was also, this PhD was based on the NWO project, which is funded by the Dutch government. So where we worked together with Avans Hogeschool and Wageningen University, who were the ones who were in charge of extracting the colorants, and they sent us the material which we had to compound, and then we did spinning to make yarns and textiles. And so for this, I started with different colorants. So the first colorants we used, the polymer we used was, of course, PLA, which can be made from starch, sugarcane. And then we used colors such as quercetin and alizarin, which can be extracted from bio-based sources, but you can also make it from oil. And then we tested both to see how they both perform in this high temperature process. And I did this using a twin screw compounder where I was just putting in the polymer material and the colorant inside, and then mix them together to make small strands, which was then being used to spin yarn. But yeah, what I observed during testing of these several colorants was for fossil-based and the potentially bio-based materials, like for example, alizarin and quercetin that was directly made by oil, it was working fine. I had a really nice bright color. But then when I was using the actual bio-based variants, I had a lot of issues because of the degradation of these colorants, because it had some sugar which was inside, which was caramelizing and getting stuck in the machines. And in the end, as you can see in the picture here, it was just brown, which was not the color we definitely wanted. So, and then with the materials, with the colorants that performed well, I went into the spinning process to make a melt spun yarn in a pilot scale or semi-industrial scale. And then I used 3 different weight percentage of colorants to do melt spinning. And then, as you can see in the picture on the right side, so during melt spinning, what we typically do is we have an extruder to heat the polymer, which is molten, and then pulled it down to make yarn. And depending on how fast we draw the yarn, we have different properties, different crystallinity, and so on. And based on this, I got, as you can see, some different materials, which was also knitted, as you can see in here, into fabrics. And after I made this, of course, when you make something, you need to test if it is good or not, or you have to have a comparison to see, is it performing better than the pure material, or is my colorant leading to some issues, which is what I did by doing some tensile tests, which is like nothing but pulling the yarn and then testing how much load it can take. And if you see on the left-hand picture here, the tenacity is the strength, ultimate strength, tensile strength of the filament, and I used 3 different drawings. So I had 3 different speeds with which I was drawing the yarn, and as you can see in the picture, my strength and my elongation were varying depending on how much I was drawing it. And on the right side, it shows a set of materials which was with 0.3% of colorants, but then under the same process as the pure PLA. And if you see there, upon addition of colorants, you don't see any big change in terms of property, in terms of strength or elongation, which is the outcome we also wanted. And which means the mechanical properties were actually affected more by the processing that I did and lesser by the colorants I was using. And the same way, I also did the thermal stability test to see how crystalline the material is the glass transition changing, or is there any other changes or like different structures of crystals forming. And what we noticed was, again, in the left side picture, if you can see the TCC point, you will be able to notice that the curve is starting to shift more towards the left side, which means there is a small change happening, but that is because of the processing. And on the right side, if you see the picture, it is more or less looking the same, which means the colorants that I added did not really affect the properties, but it's the process that I was doing, which was one of the major shortcomings of the conventional dyeing process, because in terms of bath dyeing, since you use like a water bath to dye the materials, there is always a chance that you are actually degrading the material, which could lead to loss of strength and so on, which was not happening here. And so as a short gist to whatever I was doing so far, so if you look at it, my initial idea was to start with the bio-based colorants to see how they are functioning. What we noticed was it was a lot of the times not really thermally stable. The sugar was a problem, and yield also during the extraction was quite low, which was notified to us by our partners. They could only get like 10% of yield, and whereas the fossil-based variants were actually quite stable. Like even if it was the same molecule, instead of being extracted from the natural sources, if it was made from oil, the molecule as such was stable. And so this was actually the thing that probably a chemist would be able to solve, and unfortunately, I'm not really a smart chemist myself, so I thought, why don't I look into what else I can do with the colorants I have in my hand? And then I reminded myself that one of the main things, if you are from Southeast Asia, you would definitely know this cream I have put in here. It's called Vico turmeric, which is made out of turmeric in the form of a paste, which is quite antibacterial. And every time we have like any kind of, let's say, small burns or cuts or whatever, that's what my parents used to give me and say, just put this on, it'll be fine. And then I thought, yeah, okay, so if I'm going to work with colorants, why don't I see what else can it be used for apart from just coloring? And then the other part of colorant is that if you look at pigments like carbon black, it's one of the commonly used black color pigment, which is also conductive for use and being used for anti-static fabrics. So this was the second functionality I learned. And if you could see at the chemical structure of the colorants, you always had functional groups, which meant they could also be more conductive than the polymer I'm using. That's what we wanted to look into. And then at the same time, we had the COVID outburst, and I was home for a couple of months. Of course, everything was shut down. And then I was looking at like, okay, where can we use this? And then when you look at during the COVID time, there was such a huge increase in the amount of masks that were produced. And when you look at the masks, they are usually produced with polypropylene and has quite a bit of carbon dioxide emission per mask that was produced. And the predominantly used process is melt blowing, which requires high pressured air, which means we needed a lot of energy to make these masks. So luckily, I had a colleague of mine who finished her PhD 2 years ago, and she was working in a process called electrospinning, which can also be used to make such thin fibers, because for mask, you need a good source of filtration, which means you need fibers in the micrometer or less than 1 micrometer range. And this is a process that is now upcoming and developing to produce such fibers. So it's nothing but you take a polymer melt in a syringe as a simple step. You push it through the nozzle, and you have a collector plate that is charged. And then the electrical field, the polymer then interacts with the electric field and gets stretched to form yarn, or the filaments. And then what we needed here was good electrical conductivity and good flow behavior, which meant lower viscosity. And the idea was, why don't we mix these two? And of course, for mass, antibacterial is always good. So the idea was to check how do these colorants work in this environment. And that was actually the start for the second part of my thesis. And this is what I did for the second half of the thesis. And then we had a pilot scale electrospinning machine in-house, which has 600 nozzles. And I performed trials with various colorants first to do a small proof of concept test to see does it actually work the way I want it to. And then I measured the diameters and saw it was actually working. That was quite promising. And then in the end, I started from lab scale, where I was working with 2 to 3 grams of material, and went into a larger scale where I was working with, let's say, 0.5 kilo, 1 kilo of polymer. So also not still industrial scale, but the process is still in its niche market, and it's still upcoming. And during this, I did the electrospinning trials, and as you can see in the picture and also here, so these were some of the samples that I made, especially with the colorants alizarin, quercetin, and curcumin, because from the list of colorants I was working with, these 3, according to literature, had some antibacterial activity. And when I did the trials, I of course did different process parameters and to see how can I influence the diameter, how can I make it as thin as I want it to be. And what I noticed was, under the same processing conditions, let's say temperature, how fast I'm doing the process, how much electrical. I'm sorry to interrupt, but we have to evacuate the building. Oh, okay. This is new.
Oh. So we're going to interrupt the session because there is a fire alarm. So we're going to pause for as long as it takes.
Yeah.
Naveen has with the regulations about what happens in the space.
Bit of fresh air.
Okay, welcome back to everyone. Yes, so that fortunately didn't take too long, but it's quite exceptional to have this happen during the ceremony. Yeah, sorry that you got interrupted in your talk. Fortunately, it's during the talk, so you may still continue, of course. Yeah. And we're just going to extend by the 5 minutes.
Yeah.
Yeah?
Yeah, no problem.
Okay, so please pick up where you feel comfortable. Yeah.
So I guess that's a one-time thing. So still something to remember by. So then I would like to go back to the presentation. Thank you, Prorector. So if you look at the graph in here, so we did the trials, and then I measured the diameter of the filaments I made. As you can see in the picture here, so for the same processing conditions, in terms of pure PLA, I got like 30 microns with higher throughput and 15 microns with lower throughput, which then dropped down to close to 15 or like, let's say, less than 10 micrometer when I was adding the colorants, which was also the intended outcome that we wanted to have, because we wanted to go lower with diameter so that it can have better filtration efficiency. And on the other hand, the second thing we focused on was to see if I can add one more functionality, which was to test against to have antibacterial functionality. So we tested against a gram-positive and a gram-negative bacteria using a standard method. And then if you see on the left-hand side picture, so we took some bacterial culture plates. So we made a bacterial solution where we dropped in first the colorants as such. And then we checked how good is it in killing these bacteria. And as you can see on the left-hand side picture, so this is against a gram-positive bacteria called Staphylococcus aureus. And if you see in the picture, at concentrations of over 10 milligram per milliliter, the colorants were quite effective at killing the bacteria, especially curcumin was really effective. And then we did the same test against the same bacteria with the samples that I made, with the non-oven sheets that we had. And then as you can see, if we count the number of colonies, you see as the dots is the number of bacterial colonies that we have. And if you look at these colonies, we could see that in terms of all the other pure PLA and the other colorants, we didn't really have any kind of antibacterial effect, but with curcuma, we did have it. And as you can see on the picture on the left side, among the other colorants tested, curcuma was also the most promising candidate. So, which meant it was quite a positive outcome that we were hoping for when we did these trials. And as a short conclusion and outlook, what I did during my first part of the thesis was to do the dope dyeing of the PLA to make, let's say, something similar to a knitted sock. And that was quite successful. The potential bio-based colorants were working quite well. However, the bio-based colorants are still not up to the mark as we would like to have it. So this might still be something where we need to work on the purification of the colorant and extraction step. And so this could be something that is good as a follow-up. And as the second outcome for the electrospinning, the colorants actually have a potential to work as multifunctional additive, and addition of these colorants actually led to the effect we were hoping for. We had lower diameter and also antibacterial functionality. Of course, it has not been tested against a variety of bacterium and viruses and so on, but this is already quite a nice step in a really nice direction. And so, of course, the next step for this as a follow-up would be to prototype and test the performance of these non-ovens that were made, and also investigation of other colorants or additives that could be used for such antibacterial applications. So with this, I would like to thank everybody who's here for their kind attention, and I would like to give the mic back to Prorector. Thank you.
Yeah, thank you very much for your clear presentation, and despite the interruptions. And let me also use the opportunity to welcome the audience here and also online, because it's also live streamed. I would like, before we continue with the opposition, I would like to introduce the supervisory team, who is on the other side of the table. And that will be Professor Zijde. He's from the Maastricht Institute of Biobased Materials, that the candidate is also from. and Professor Groten, who is from Hochschule Niederrhein in Germany. They will not be asking questions, so that's, in case you were wondering who they are, I will not otherwise introduce them. My name is Ralph Peters. I will be acting as the pro-rector today, which means I'm replacing the rector and guiding you through the ceremony. So then now it's time for the opposition. And I would like to start with Professor Jockenheuvel. He holds a chair in biohybrid and medical textiles here at AMEBM, also at Maastricht University. Please, Professor Jockenheuvel.
Yeah, thank you very much. Dear candidate, first of all, congratulations to your nice work. I have really enjoyed reading your thesis. Nice work, and I learned a lot. Let's come to the first question. As you know, I come from biomedical, and we're doing a lot with electrospinning. So you make melt electrospinning. We mostly do solution e-spinning. Can you explain me the difference? Is it just two sides of the same coin? Where are the pros, where are the cons, where are the parallels between both processes?
Highly esteemed opponent, thank you for your question. Yes, so we, of course, work, as I said, with this melt electrospinning. So when we look at the difference between the solution electrospinning and melt electrospinning, so in terms of electrospinning, what we do is like we just need like a polymer liquid, which will then be pulled down using a collector plate to make a filament. In terms of solution electrospinning, we work with polymer solutions. For example, here we work with PLA, and in terms of PLA, chloroform or dichloromethane could be potential solvents that one could use for solution electrospinning. And once, say, roughly 8–10% of polymer solution is made, which is then pushed through the nozzle, and then the filament is formed through evaporation of the solvents, and the polymer is crystallized through the evaporation of solvent. And in terms of melt electrospinning, we go to much, much higher temperatures where we directly melt the polymer, and we push it through the nozzle, and then the polymer melt. As it cools down, it crystallizes to make the filament. The pros and cons for the process would be, since polymer solutions are expected to be more polar in nature, so there is a high chance of achieving filaments of lower diameter with solution electrospinning, and also polymer solutions have much lower viscosity compared to polymer melt. So for electrospinning, we need lower viscosity and higher electrical conductivity, which is something we get from the polymer solutions, which means we have diameters in less than micrometer scale already. And in terms of melt electrospinning, since we start from polymer melt, which has like 20-fold higher melt viscosity, the issue is that we are still a bit thicker in terms of diameter. Of course, but you don't use solvents, which means melt electrospinning has the potential to be more greener and can also have higher productivity, because essentially instead of having, let's say, 10% of the production you do being fiber, you have the entire fiber. Of course, we are not there yet, but these are the potentials that melt electrospinning could offer.
Okay. So you use it already for medical purpose, but where could be then the limitation of melt electrospinning with regard to the drugs, for example, you would like to integrate into your fibers?
Yeah. Thank you for your question, highly esteemed opponent. That is a really fair and very interesting question. So, of course, melt electrospinning also has this disadvantage that you have to go for a high temperature for the process. So a lot of the antibacterial drugs that need to be used may not be high temperature stable, which would then be the disadvantage when we also go for more biomedical applications. But probably for making like filtrations, like air filters, this might still be a good option. But for, let's say, if we look into more in vivo, like something that needs to be used inside the body, or like some really drug delivery kind of applications, melt electrospinning might fall short because of the temperature issues.
Yeah, proteins would be cooked eggs, yeah. At the end, that's correct, thank you. When we're talking about electrospinning, if I talk about solution electrospinning, the moisture, the humidity is always a very important factor. How is that with regard to melt electrospinning?
So, Yes, here also we had issues with some melt electrospinning because of the humidity, because the behavior of the material is also, of course, different based on the humidity we had. Sometimes when we have like really high humidity, we were also getting, let's say, flashes or short circuits during the trials. So what we also tried to do was like, of course, unfortunately, we didn't really have like a climate chamber to control the temperature and humidity. But so every time we did the trials, we tried to make sure we had like close to similar conditions, and we also were doing the trials in a single day to try to make sure that you have the impact of the environment, to keep the environment of the impact as minimum as possible.
Do you also get this kind of, if you have a high humidity in solution electrospinning, you get really porous fiber, so really the fiber itself is porous. Do you get the same results also with the melt electrospinning?
With melt electrospinning, we didn't notice that. So it was just solid fibers irrespective of the conditions. So we normally only had fibers that had no pores in them.
Okay, thank you. Perhaps my next question, I need one Paranymphe, perhaps Paranymphe Siebert. Could you please read the last but one about the scale of experimental matter?
The scale of experiment matters. One cannot simply plan a scale-up expecting the same behavior and complexity.
What does it now mean for such a complex process like electrospinning?
Yeah. Thank you so much for the question. That's also a very important point. What we noticed was like when we were like going from lab scale, where we were starting with some grams with single nozzle, with a single collector plate, it was much easier to, let's say, control the process and change parameters as in however we like to do it. And it was much easier to also check the results immediately and so on. And when we go now for the higher scale process, the first thing we noticed as a difference was the dwell time that we had in the extruders, because in the lab scale process, we had roughly a dwell time of close to 2 to 3 minutes, maximum 4 minutes, and the second we went for scale-up, it was just almost 10 times higher, which meant we had more chances of degradation. And also, in terms of lab scale process, we had only one nozzle. For the pilot scale process, we had 600 nozzles, which meant the interaction with the field was also a bit different. And the main thing we also noticed was the whipping, because when the single nozzle, the collector plate was like 11 centimeters. So the whipping was almost for the entire plate. Like the sample size was also almost 11 centimeters. And then when we went for the scale-up process, the amount of whipping that could happen also depended on the distance between the nozzles in the spin plate, because now suddenly it's limited to a couple of centimeters. And then we also had cases where it started building like a tower on the top because it couldn't whip further. So things like this also led to more complexity in the processes, which could not always be judged based on the small-scale experiments.
And with regard to upscaling, there are other productive processes also making non-woven structures. Where would you put your technology?
So,
from the productivity, from the ecological point of view, whatever.
So from a technological point of view, I would suggest that it would be better to go more into filtration application, because that would be where such small filaments could be helpful. Or at this point, again, we are not there yet, but if we actually manage to make some really nanoscale fibers, this could also probably be cut and maybe used for reinforcement applications, which might also be a potential application where I could see this working.
Thank you very much.
Thank you, Professor Jokkenheuvel. And what I would like to mention still is he was also the chair of the assessment committee. Then the opposition will be continued by Professor Regard, who was a member of the assessment committee and also acting today as the secretary to the degree committee. She also a chair on circular plastics, and she's with the Department of Circular Chemical Engineering here at Maastricht University. Professor Regard.
Thank you, Pro-Rector. Dear candidate, thank you for your introduction and also for your thesis. I have learned a lot about dyes and melt spinning in reading it. My first question jumps to your chapter 6 on the melt spinning process, which is relatively fast. And you speak there about the potential post-crystallization of your material. And you write yourself that unless they are relaxed properly, this will give a shrinkage problem. But you don't elaborate on relaxing properly. How do you see that? What is this? How is the process? And how would you improve it?
Yeah. Highly esteemed opponent, thank you so much for your question. Yes, so that's quite a nice point. So in this case, what we did was, like, when we do the melt spinning process, since it's a very high-speed process, for a slow crystallizing material like PLA, what we observed was, in a typical spinning process, what is done is we have like a spinneret, holes where the filament comes out, and we take up, and then it's normally directly winded if it's like to make like partially oriented yarn. But what happened in case of PLA was, when we did the same thing without applying any temperature to in the process, similar to what we did for PET, what happened was the material was completely crystallizing and like relaxing inside the bobbin after it was wound. And over a period of time, if it was only like some half a kilo of yarn, it shrinks so hard that we couldn't get the bobbin out. But if it was going over 1 kilo, at one point the bobbin just exploded because of the shrinkage forces was so high that it couldn't handle itself. And as a remedy, what we looked into was to use temperature to relax the yarn, because if we manage to, let's say, make it go to an equilibrium state, because when we stretch, we apply a lot of tension on the material, and we wanted to then relax it, and then temperature was the way to relax it, one. And in contrast to a typical spinning process, what we did was, instead of having just one pair of gordets to pick up the yarn and wind it, we included three other sets of gordets to increase the path before it was wound, and gave temperature in each of these steps. So we tried to keep the filament at over the glass transition temperature to make sure there was sufficient time for the material to relax before we were winding it. And this helped us solve the problem.
And what exactly are you doing in the polymer structure during those heat steps?
So I would expect that we crystallize the material during this relaxation. So when we stretch, we orient them, but then they are still again oriented under tension. So what we noticed was, when we had the temperature and then relaxing and then winding, the crystallinity was also a bit higher, of course, because of the temperature that we used, in comparison to when we actually did the take-up and wound it directly, where the crystallinity was also much lower.
Okay, thank you. You have a lot of attention for sustainability. It's in your title. I want to talk a little bit about recycling. In recycling in general, dyes are considered an immense problem because they tend to create all sorts of volatiles, and I'm talking about mechanical recycling. If you have your beautifully dyed PLA textiles and that would be recycled, it goes back into an extruder, what sort of funky things are going to happen?
That's a very interesting question. Thank you, highly esteemed opponent. It is true that dyes are definitely going to create definitely creating a lot of problems when we go for mechanical recycling, especially. But then, in general, in terms of textiles, dyeing is also mostly done in bath dyeing process, where the dyes that are used are also not extremely high temperature stable. So the bath dyeing is normally around 100-150 degrees Celsius. For PLA, even less than 100. So in this process, the dyes that we use are one of the primary tests we are doing is the thermal stability of the dyes when we do the processing. And since we already melt it to mix it once and then spin it, I could say like that the dyes are actually stable at this temperature, which means for recycling, it could also show a potential that like it might not be as bad as the other colorants that are currently being used for dyeing at low temperature. So we are already using ones at high temperature, which gives an advantage that this process as such has very less water requirement. And when we now talk about recycling, since it's already is able to sustain the high temperature process, I would expect that it should be able to go into the extruder also for the second time.
That's a very bold statement. I would also like to call on your paranims to read out the last proposition.
Okay. Bio-based and biodegradable does not always mean sustainable. What is sustainable depends on the specific use scenario. Circularity, GWP, carbon footprint.
Thank you. I could discuss about this for hours, but I have 4 minutes. I would like you to elaborate a bit on that, and not so much talking about carbon footprint, but in the sense of where in the system for textiles, do you see a sustainable place for bio-based, biodegradable textiles?
Thank you so much for your question. As you have already pointed out, this is such a topic that is actually open for a very, very elaborate debate. As an example, I could think about some applications where we cannot reuse the material. For example, like tea bags. If we look at tea bags, what we currently use is mostly cellulosic fiber and then PP together with it. But then once we use the tea bags, it's also extremely difficult to split the materials as such and then recycle it. So, and we already have tea powder, which are also biodegradable, and we are going to most probably put it away in a waste container. So,
okay, but talk about a textile that needs dyeing, because that is the focus of your thesis.
For dyeing. So what it could be, where it could be useful could be maybe, let's say, for apparels, for example. If we have like microfibers that are being created during washing, so that might be a potential place where degradation should be better, because we might then have lesser issues with microplastics. In terms of bio-based colorants, there is also definitely one more thing that needs to be, let's say, focused on, because that would be more on how green is actually the extraction in comparison to, let's say, fossil-based materials, because that is why I would also, let's say it is not always sustainable, because that is dependent, of course, on how much of material I need to make the amount of material I need. And in terms of use case scenario, I could say that, let's say, like textiles and T-shirts, for example, that we are wearing could also be an option, like cotton, for example.
Yeah. Thank you, dear candidate. That's all for me.
Thank you, Professor Regaard. Then the opposition will be continued on the other side of the table by Dr. Dolmans. He was a member of the assessment committee, and his expertise is in melt spinning, and he's with industry with the company Oerlikon Barmag in Germany. Please, Dr. Dolmans.
Thank you. I thank you, candidate, for your thesis. I really enjoyed reading it. Also, the analytical part. I'm a fan of the rheology, the melt rheology, which is very important in melt spinning processes, of course. To my astonishment, and also yours, you described it here, adding a master batch or adding a dope to the PLA increased the viscosity. And your explanation says that it might have to do with anchors and hydrogen bondings between the polymer chain and the molecules. And you've proven it with the FTIR. Can you elaborate, or can you think of other experiments or kind of ways to prove this? Because the FTIR is one proof, but is there another way to prove that the hydrogen bond is affecting that?
Highly esteemed opponent, thank you so much for your kind words and also the question. To be honest, I cannot really directly think of another way where I can actually confirm the existence of hydrogen bonding, because I'm not really a chemist, unfortunately. That was one technique I knew where we could look into this. And there was also one more reasoning behind why I thought of this anchor thing, because in this case, we use PLA, which is a much high molecular weight polymer, which is in a melt form, so it has a high viscosity. And we are using colorants, which are smaller molecules. And let's say if it were to dissolve in the polymer, for example, then I would expect that we would expect that the viscosity goes down. And in this case, we didn't really have any reduction in viscosity, which meant the dyes were actually not dissolving. It was present as the particles. And of course, one of the main reasons is that I expect that the viscosity increased was because the dyes were neither melting nor solubilizing, because among the dyes that I used, curcumin was melting almost at the same temperature as PLA, and in that case, we had drop in viscosity at higher percentages of curcumin. So there we definitely had the effect that it might not have been because curcumin is soluble, but it is more because curcumin melted in the processing temperature. So I would expect that led to the lower viscosity in that case, but in the other cases, it was mostly just the anchor points, which was not really ready to flow.
And the follow-up question on that one, because at a certain point you say at higher shear rates, the anchors get loosened and then viscosity drops, and that also creates a better melt spinning process. But in your rheology experiments, you are increasing by the angular speed, or frequency, you are increasing the shearing forces, and you do not see that in the curves. Because one would expect another more steep incline of the viscosity curves, so that doesn't add up in a way.
Yeah. Thank you for the question and the point that you mentioned. It is true that we don't always see that in the viscosity curve that the viscosity drops. So what I used here for testing was more of a parallel plate rheometer. So we were limited to how much shear I was able to apply in this case. And in a capillary rheometer, we would be able to go to higher shear rates, which is very much more similar to what we have in terms of a spinning process. So what we noticed in these graphs was that the viscosity starts higher, but then you could always see a tendency that it starts to go down, but almost meeting at the same point. So what I would say is that we are not, right now actually not in the shear that we applied in this, in the range of shear that we apply in a spinning process, but lower than that. Yeah. So depending on the trend, if we look, I would still expect that they actually meet more or less when we are actually at the higher shear rates, because the tendency is something we notice in that.
Okay. Would be interesting to see, and you most probably have them, the storage, the shear storage and the shear loss modulus. Might be that you see a difference in that one, and that would also be the experiment that I would suggest. A follow-up question on the melt viscosity and the GPC analysis, molecular weight. You have done this, and you state that there is no significant difference between the molecular weight of the pure PLA and the dope-dyed PLA. Could you explain what you mean with significant?
Thank you so much for your question. Yeah, so in this case, we mean, so since when we do this GPC analysis, we don't measure the direct molecular weight, but we measure more of a relative molecular weight, which means we have a standard of PMMA, and when we look at the molecular weight of PLA, so in the process we have a molten, a polymer dissolved in a solvent, which then goes and hits a collector, where we see how long did the PMMA molecule of a specific chain length take to achieve, hit the target, and how long does PLA molecule takes to hit it, and we calculate that back to a relative molecular weight. And since we do it in a very more relative way, there's also a possibility that the chain length and conformation of PMMA and PLA are different. So there's always chance that minimal changes in the molecular weight can actually come from this. So normally 5 to 10% is something that we could expect as a difference because of this behavior. And what I noticed in the GPC that I did was we of course had pluses and minuses, but it was never really over molecular weight of 10,000 gram per mole, which is what I would expect to be a significant reduction in molecular weight. And if we do have a more significant reduction in the molecular weight, it is something I should be able to see in rheometer. And what we noticed was with the dyes, either the viscosity was the same or it was higher, which meant I was not really having a huge breakdown of PLA molecules. So the conclusion that there might be some degradation, of course, because every time we have a high temperature process with shear, that is going to be degradation. And as long as it is not to an extent where I'm going to have a complete loss of properties or it's going to flow like water, if it could be controlled in a point where I can still use the material, that is something that we can still work with.
Thank you.
Thank you, Dr. Dolmans. Then the opposition will be continued by Professor Oru. Professor Oru holds a chair in organic chemistry here at Maastricht University at the Maastricht Institute of Biobased Materials. Professor Oru.
Thank you, Chairman, for giving me the opportunity to discuss with you, dear candidate, some parts of your thesis. An impressive piece of work, and as I'm an organic chemist, it was difficult to find some organic chemistry structures in there, but I managed, and in the process of doing that, I also learned a lot about all the process engineering part that you did. But you probably understand that my focus will be on the organic chemistry. So I had a question on, pages 103, 104, and 105 first. That's in chapter 3, where you, let's say, investigate the conductive additives to the properties in the polylactic acid fibers that you are producing. And the first thing I notice is that you are using L-lactic acid. So you're making, let's say, a stereo-specific polylactic acid, let's say, polymer. And then I look at the structures of the, let's say, colorants that you are adding. And one of them, especially, hematoxylin, has stereocenters in there. So did you see any, let's say, effect of, let's say, interaction between the stereo-specific polymer L-lactic acid on one side, and on the other side, the hematoxylin on the other side?
Esteemed opponent, thank you so much for your question. That's a really important point. So as I'm not really an organic chemist myself, let's say, might not really have a direct answer to that, to be honest. But there was one specific thing that we observed with the hematoxylin molecule, and that was that among almost among all the colorants that I was using, I could actually see only degradation in terms of hematoxylin, where I had quite a large drop in molecular weight. I could suspect maybe that is a reason that could come from this difference in the stereochemistry, but I am, to be honest, not in a position where I can say if that caused it.
Well, it's good that you mentioned this. I don't think that's caused by the fact that this is a stereo, let's say, specific molecule that you are using. But if you look, that's my thoughts, at the structure of hematoxylin, it's hemiacetal. And under, let's say, slightly acidic conditions, it might ring open. But that's another discussion, probably. But anyway, it would be interesting to look at the stereocomplexation of such molecules with your poly-L-lactic acid, because that might also really impact the conductivity properties. But maybe something else, and that's related to the structure of quercetin, where you have quercetin is a flavonoid, and it's also used a lot as a antioxidant in, let's say, reform applications. You can go to the reform shop and then have all kinds of health things connected. But often this colorant and also the health properties are connected to the glycoside of quercetin. Do you know what I mean with the glycoside of quercetin?
Fortunately, no.
So then I explain you. So if you look at the structure on page 105, maybe you have to get the thesis.
Yes.
You see the hydroxy function next to the ketone in the structure, and there a sugar molecule or more than one sugar molecule, typically glycose, but can also be others, is attached. So I was wondering, if you are using bio-based quercetin, how sure are you that no, let's say, remainders of this sugar part are present during your, let's say, experiments?
Yeah. So thank you so much for your question. So it is true that indeed, like, if we have sugar parts, what I would expect is that, or we had that in terms of the other bio-based colorants that I was using, so where this sugar was actually degrading at higher temperatures. So if we would have something like that in here, I would expect that it probably also degrades at the processing temperature that I was using. And that was something that we could definitely notice, because half the time the screws were jammed because of caramelization, and we had to open the extruder completely to clean it. But I think in this particular case, I think I also worked on the direct bio-based variant where I had this issue, but I also bought the same molecule from Sigma Aldrich, which was oil-based, and the molecule as such was stable at high temperature. So of course, once these saccharide side groups are, let's say, removed, it should be then good for using at the high temperatures.
Yeah, when it's fossil-based, it has, of course, another glucose attached. So maybe when you use bio-based, let's say flavonoids or etc., you first have to deglycosylate before you use them, which is also a chemical step, which also might not be that clean. So maybe one more question, if I'm still allowed, which is on, I think, page 167. There's also a couple of organic chemistry structures. So, and this is focusing around the curcumine that you use, and you found that you have nice, let's say, antibacterial properties in the materials that you then make. So I was just wondering how the interaction between curcumine and the polymer could, let's say, could work. And if you look at the structure, you have this carbon atom between the two carbonyl groups in the middle. So, and it's known that this is a very, let's say, reactive position. So did you see any covalent bonding between curcumine and your, let's say, polylactic acid material? Or is it only hydrogen bonding, as you mentioned before in the question with my predecessor?
Thank you for your question. I think that is probably something that is definitely possible, but I would think that based on the results we have in here, we don't really have any direct reaction going on, because we didn't also see any change, like significant or noticeable change in terms of the FTIR. And what I also noticed was only a small drop in the viscosity of PLA, but not a lot of degradation also, which means, or if we have, let's say, reaction, it could also maybe lead to a higher molecular weight, which was also not the case. And the change in viscosity was also more similar to what could happen when it was more of a plasticizing effect than a degradation or any new chemical bond formation. So I would expect that it was most probably just hydrogen bonding that we had.
Okay, thank you. Mr. Chairman, I'm satisfied.
Thank you, Professor Oro. Then the opposition will be continued online. We have Professor Meijer with us. He's a professor of photonics and material science from the Hochschule Hamm-Lippstadt in Germany. Professor Meijer, please.
Thank you, Pro-Rector. Dear opponent, thank you for your thesis. I also enjoyed reading it, obviously, as everybody else did. And of course, I do have some questions. The first question is maybe a bit off-shot. I was wondering, you were very interested in sustainable coloring of materials. And of course, the most sustainable coloring would be without any colorant, so without dye. Can you think of ways to color a material without using a dye at all? It's not a joking question.
Highly esteemed opponent, thank you for your question. That's true. So indeed, having something which is more intrinsically colored might be a solution to, let's say, the entire dyeing problem. What I might or I could expect is maybe making some small changes in the chemical structure of the polymer to include groups similar to what we have in terms of colorants to, let's say, make the polymer intrinsically colored. So in that case, we might not have an extra dyeing step that is necessary. For instance, like in terms of polyamides, we have already like a natural, say, a bit yellowish kind of a color. So I would think that something like that might be a solution to this, to have like maybe include like chemical changes inside the polymer chains to give us a bit of color intrinsically from the structure itself.
That's of course a good possibility, but I was thinking of something nature does. For example, there's a certain type of butterfly which is brightly blue colored, but there's no pigment at all. It's not in its structure, but it's something else. It's what you can get by interference. Can you think? Is it known that there are fibers or textiles which get their color from interference? Is that a viable possibility, or is it just a nutty idea from the eastern part of Germany today? Yeah.
I think it might be a bit far-fetched right now to have such directly, let's say, intrinsically chemically modified material, because it might also make it difficult to, let's say, polymerize it to a molecular length where we are able to spin it. So yeah, I think it might be a bit of a far-fetched idea at this point to, let's say, have intrinsically colored material through some incorporation of chemical groups. But what I know has been done is, for example, PLA was, like, say, grafted with carbon black to make intrinsically colored material. So there is a possibility to do this, but I think I could probably find maybe only 1 or 2 papers which tried something like this, where they grafted a color molecule to the polymer directly and they were directly spinning with it.
Okay, so I understand it's too far out. So we have to stick with dyes and pigments for coloration as of now. My question would be, if you're looking at the recycling process and you think about the necessity to maybe remove colors before you mechanically recycle a polymer, would you see an advantage of dye doping, or would you see the advantage rather with a bath doping if you have to remove the colorants?
Okay. Thank you so much for your question. So I think in this case, having a bath doping, it's a bit hard to say, because it depends a bit. Because in terms of dye doping, we don't really add extra chemicals to fix the dye molecules or onto the surface of the polymer. So it is intrinsically mixed, so it's inside the polymer as such, which might also make it a bit difficult to extract. But in terms of bath dyeing, what we use is like some, let's say, bit of chemicals to fix the dye onto the surface of the filament, which might also make it possible to reverse this reaction to, let's say, remove the colorant. So I think if we want to look at recycling where we want to remove the colorant completely, maybe bath dyeing can be a better option. But if we look at, let's say, mechanical recycling, since a lot of the dyes used for bath dyeing are actually used for dyeing at low temperatures, and when mechanically recycled polymers are directly molten, so you need to have much higher temperature for dyeing. So I would expect, like, if you don't have to remove the color, dope dyeing could be the more or the better alternative.
So that would mean that you wouldn't remove color, but you would sort used material by color and then recycle it color by color.
Yeah.
And then then it might be worthwhile to look at a limited amount of colorants. Is that true? So that you can make red by maybe an almost unlimited choice of colorants. So it would be good for such plastics, if you're looking at mechanical recycling, to just have one or two colorants for the recycling process.
Sorry, I couldn't hear you properly. Can you please repeat the question?
I'm sorry, yeah. What I'm thinking about is, if you would limit the amount of dyes to use for dope dyeing, it would be easier for the recycling, because you would then not, you could just sort colors and you would know the doping dye used.
So much for your question. Yeah, that is definitely true. So let's say, like, to make most of the colors we need, I would say having RGB could definitely give us all the possibilities of colors that we want to make. And as you suggest, point out, what we could do is like limit the dyes. Let's say for red dye, in terms of PLA or PET, for example, we say this is a dye molecule that everybody uses to get the red color. And for same for green and blue, we just fix on one best performing molecule, and then it might also become easier to have different colors by, let's say, mixing in different amounts of each of these colors, which would also give us, let's say, for design for recycling a bit more, a bit less complicated, because then we know which molecules we're exactly looking for, and that could also make it possible to make it easier to remove it.
Naveen Balakrishnan, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room. I adjourn.
All right, please.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. All your time, cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you won the battle once you've grown. South side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. fly by now, don't waste all your time. 'Cause I'll go the extra mile.
let me reopen the session. Naveen Balakrishnan, the degree committee here present has assessed the quality of your thesis in your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Zijde is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
All right, please.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I do.
By the authority vested in us by law and in conformity with the decision of the committee, here I present you, confer upon you, Naveen Kumar Balakrishnan, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Congratulations. And now it's time for... Now it's... Yeah. Congratulations again, Naveen, after a long travel, a long journey. As every journey has up and downs, but that's not what I want to talk about, up and downs, that's in every PhD. But it's a long time ago that we were sitting at Aachen, and there was the discussion of, do we go to Maastricht to set up a new group? And then you were one of the first people starting from Aachen to Maastricht to set up a new group, a new institute, without machine infrastructure, empty labs, nothing. And so in your travel, in your journey, was not only doing a PhD, but building up a whole lab. So thank you very much. I know that's an additional work that you had. We know you as a very strong team player. You keep the lab running, you try to replace high. You are in between deep research and repairing extruder screws. So that's a very broad spectrum that you have there. Yeah, and you know every machine in detail and your topics in detail, as we saw today. That's a really strong achievement over a long period of time. Thank you. In the last year, you started to do, before you finished your PhD, postdoc work. So one point is you massively increased the industry contacts and service agreements with the industry. That's really strong. That brings money to repair extruder screws and all that, what we need. And that was necessary. That is much stronger since you are there and since you do that. So thanks for that. You are supervising the PhDs together with me. So I feel that in daily life that many questions go directly to you. Thank you for that support. And since over a year you are running the AMIBM e.V., the German entity, with all these bookings, reminding me for salary transfer and finance management and all this work that has to be done. Yeah, and you will stay with the group for a while. I'm looking forward to this time together with you. Thank you very much for your support and thank you very much for your work. Congratulations.
Thank you. Thank you.
Dear Dr. Balakrishnan, also on behalf of Maastricht University, I would like to congratulate you with the doctor title that you acquired. And I would like to extend my congratulations also to the family and friends and colleagues here present, maybe online. And of course, my congratulations also to the supervisory team. Well, then hereby I close the official part of this academic ceremony. There's a few household comments I would still like to make. So what we're now going to do next is take some pictures here. And you can also have a final word with our opponent from online from Germany, who's also here. So we can congratulate each other and say goodbye. And the audience can already go to the hall, because there we will then also reconvene to make another picture. Of course, family can stay here, and then let's switch to the festivities. Thank you all.
Thank you.
Recording stopped.